Most software engineering today relies on a comforting fiction. We treat compute, databases, and even complex AI models as clean, isolated black boxes. You send a request, and you get a deterministic response. In the convergence of AI and quantum mechanics, hiding the physical reality of the machine has become a liability. Standard classical architecture assumes perfect hardware obedience. Look at this server rack. The physics of the silicon are entirely hidden beneath the software layer to ensure developer convenience. Deep tech strips that away. When you are operating at the absolute limits of computational physics, hardware constraints directly dictate your algorithm's viability. If you do not understand the metal, the code simply will not execute. Transitioning into systems architecture at this scale requires traversing the entire stack, from the behavior of analog qubits up to the orchestration of agentic AI. In this environment, relying on abstraction is a blind spot that leads to systemic failure. We start at the physical layer. A physical qubit is not a discrete digital bit, cleanly holding a 0 or a 1. It is a continuous, unstable analog system. Instability creates physical deadlines, called coherence times. T1 measures energy relaxation, while T2 measures dephasing. Exceeding these limits causes state collapse. To execute code, finely tuned microwave pulses are fired. Signal processing shapes these waveforms to intercept and realign the decaying qubit. Control electronics manage this process, while constantly fighting thermal noise and electromagnetic crosstalk from neighboring qubits. Quantum software execution is a race against physical decay. Moving up to the transpilation layer, we encounter the reality of hardware limitations. Developers cannot simply run abstract logic circuits on current machines. Hardware doesn't support arbitrary logic. High-level code must shatter into a native gate set, the few operations a processor can physically perform. Additionally, hardware has limited connectivity. To connect non-neighboring qubits, swap gates must move data across the chip, step by step. This swap overhead is a critical bottleneck. Every extra gate added to route data increases the total circuit depth. When this expanded circuit depth takes longer to run than the T2 coherence time we established earlier, the quantum information vanishes. Without hardware-aware compilation, a mathematically perfect algorithm will output nothing but physical noise. This brings us to the difficulty of scaling. Quantum power is not increased by simply adding more physical qubits to a processor. Reliable computation requires quantum error correction, which relies on the stabilizer formalism. The stabilizer formalism is a mathematical method for measuring errors in a system without collapsing the quantum information itself. This forms the basis of a surface code. Qubits in a lattice constantly check their neighbors to identify and mitigate analog errors. The math is demanding. Creating just one reliable logical qubit requires trapping and managing over 1,000 noisy physical qubits. This massive physical overhead is why legendary algorithms, like Shor's for factoring large integers, cannot run on today's noisy hardware. Achieving quantum advantage is a massive, classical distributed systems problem. Quantum algorithms operate in hybrid loops, not as standalone executables. They rely on classical data centers to function. Take the variational quantum eigensolver, or VQE. In this loop, a classical system calculates gradients to update the quantum processor's parameters after every run. Calculating updates requires massive classical GPU clusters running sparse linear algebra, computation optimized for matrices dominated by zeros, representing the quantum state. Constantly transferring these massive state vectors creates intense memory pressure on the classical hardware. Any theoretical quantum speedup is neutralized if the classical high-performance pipeline chokes on these bandwidth constraints. At the top of the stack is agentic AI. Here, large language models move beyond simple chat interfaces to become autonomous orchestration engines. An agentic system can utilize a retrieval-augmented generation, or RAG, pipeline. RAG is a method that allows an AI to pull in live, external data, like hardware calibration and crosstalk metrics, to ground its reasoning in real-time facts. Using this live data, the AI autonomously selects the best transpilation strategy and routing the workload across distributed Kubernetes clusters. The AI dynamically adjusts classical parameters to mitigate noise, responding to hardware's behavior as it executes. Agentic AI bridges discrete classical logic with the chaotic reality of the quantum processor. These technical mechanics drive the economic reality of the industry. The bottom layers for cryogenics, fabrication, and physical hardware are dominated by CapEx, the massive upfront costs of physical infrastructure. Contrast this with the top layers of agentic AI and cloud compute, driven by OpEx, the ongoing costs of APIs and compute time. These financial forces dictate industry consolidation. The high barrier to entry for hardware creates vendor lock-in, while the high cost of running AI models drives enterprise build versus buy decisions. In deep tech, the cost of inefficient code is measured in millions of dollars of wasted physical capital. The massive capital cost of this hardware limits its development to a few global corporations and state-backed entities. This concentration of power dictates the geopolitical timeline, especially because the overhead required for error correction keeps classical RSA cryptography safe for now. However, the migration to post-quantum cryptography, or PQC, is an immediate mandate. PQC refers to new cryptographic standards designed to resist quantum attacks. Systems must transition now to protect against harvest now, decrypt later strategies, where adversaries store current encrypted data to unlock it in the future. Success in this environment requires an architect who can master the underlying math, respect the physical hardware, and orchestrate classical systems with machine intelligence. True technological power belongs only to those who engineer across the entire chasm of reality, refusing the comfort of abstraction.